This is an ant mill. It's an example of an emergent behavior, a global byproduct of the relatively simple per-agent algorithm, following the ant in front of it. But recreating this behavior, or rather any group behavior, can be really expensive in swarms of robots. It's not just the robots that are expensive. Setting things up for each experiment can be especially time-consuming and costly. And that would be fine if stuff just worked the first time, but it never does.
But that's what we have simulations for. I can run thousands of trials at once without having to worry about setting anything up or breaking anything. Because of this, we've seen complex behaviors emerge in different simulators, like this hide-and-seek game, and adding more is as simple as dragging a slider and hitting play.
Yeah, but hyper-realistic sims take a lot of time to develop and aren't flexible. And simpler simulations-only research often requires unrealistic assumptions. Real robots don't have perfect sensing or actuation. Historically, we've solved these problems by waiting for technology to catch up with what's possible in sims, or to simulate every quirk and feature of a real robot and its environment. We're stuck in a loop where the swarm research of today requires the technology of tomorrow. It's time to break the loop. And here's how. Instead of tediously chipping away at the gap between simulation and real robot, we try to over-approximate the robot in the simulator in as simple a manner as possible. We'll be demonstrating how we made this circling behavior happen with these flockbots created independently by the CS department here at our university. We've chosen a binary sensing-to-action controller that we've seen work on similar robots. The robot checks if its IR sensor can see anything. If so, it turns left. If not, it turns right. We'll just be focusing on tweaking parameters to make this work. First, we choose a reduced state model and take measurements of the robot's capabilities, its sensing and actuation limits, and gather data on their idiosyncrasies, their imperfections from a representative sample of robots with multiple trials per robot. We're using a unicycle model, so we measured forward speed and turning rate, along with the sensor range and false positive rate.
Then we take this data and program these dynamics, the environment, and the initial conditions into a simulator. At this step, we want to make sure that the simulated agents can't do anything that the real robot can't. So we approximate the idiosyncrasies, the noisy sensing and actuation, by creating a normal distribution that encapsulates the measurements we took from our representative sample. With that, it's time to explore. Using a grid search, we use the simulator to find what sets of parameters match to the swarming behaviors. Here, we borrowed a tool from the chemistry department, the phase diagram, to help describe these relationships. We chose to sweep the robot's forward speed and turning rate, ran simulations for each combination, and manually labeled each one with the behavior that we saw.
Finally, we used the outputs from the previous step to help us pick parameters to run the real experiments with. Voila, we successfully produced milling on a real robot swarm by picking parameters from the green region. But outside of that, you'll notice some disagreement from what the simulator hypothesized and what actually happens. That's actually fine. Remember, we ensured real robots were better than simulated robots. And that's how to apply our methodology if everything works perfect the first try, which it didn't for us. But the key difference of our approach is when to upgrade the robot or simulator. So when something inexplicably goes wrong, like we don't find any interesting behaviors in the simulator, or if the phase plots tell a completely different story than reality, we have a choice of upgrading either the robot or the sim. We only upgrade the robot if it's easier or cheaper than upgrading the sim. If there's a simple adjustment to make the sim more realistic, try that first.
Case in point, the collisions in the simulation were initially set to be catastrophically inelastic. Just one touch and everything would grind to a halt. So after observing how the flockbots moved in real life and that this was affecting the simulation, we decided to change the simulation to ignore collisions at certain angles. And when we suspected that our sensing range wasn't good enough, we augmented the sensing with retroreflective tape. Simple enough.
And success! Simulated swarm, real swarm. No more guessing of parameters, no taking shots in the dark.
We can formulate a hypothesis and test it.
And we save time by only upgrading things that absolutely need to be upgraded.